Hello, welcome to the introductory session on Design Assistance Tool. It performs probabilistic energy analysis using BIM and machine learning. The tool provides relevant information to support decisions for energy-efficient building design. This tool is suitable at the early design stages when several design parameters are uncertain. It has four primary functions. First, design space exploration. Second, analyze a design option. Third, compare several design options. And in the last, sensitivity analysis. Don't worry about the details. We will be looking into the details later. The tool uses Autodesk Revit for developing BIM model. Also, currently, the tool is accessed through plugin. You can access the tool by clicking here. Let's look into the interface and what's possible in this tool. Let's look into these controls one by one. Please ignore the disabled function for the time being. We can choose the simulation tool, either machine learning or Energy Plus. We will be using machine learning predictions for this exercise. It is way more quicker than Energy Plus, but slightly low accuracy. Next, there are settings to define the design space. Let us use a small definition for the design space here. Design space is defined by a set of constraints, in which a designer explores a few designs. Thus, in this context, there are spatial constraints defined in the model. These lines mark that boundaries for the building. Then, there are other parameters which are defined numerically. We can set these parameters using this button, View or Edit Parameters. Once we are in this form, we can access the complete parameter list. All the probabilistic parameters are defined by three variables: mean value, variation or standard deviation, and distribution function. I hope these variables are self-explanatory. Currently, we classify the design parameters under 5 groups: geometrical, construction, and so on. We can switch tabs to access all these parameters and modify the mean value, variation, and distribution function. For zones, we can click here to modify zone parameters. All the information about the parameter groups and parameters, their possible values, you can find in the info document. The name of the most parameters is self-explanatory. You can ask me if you want to inquire about any of these parameters. These parameters are used to define random geometry and have completely different purpose. These parameters are very well explained in the info document. You can load or save the current settings into or from CSV or JSON using these buttons. This allows to reuse specific settings later. It is better to familiarize yourself with this form. We will be using this form to define probabilistic parameters for multiple purposes. Anyways, let's move on. Now, we will be looking into design space exploration. We can set the number of samples to be generated for design space here. And the sampling scheme can be chosen here. 3 supported sampling schemes are Latin Hypercube, Sobel, and Monte Carlo. Each sampling scheme has few advantages and disadvantages. Among these, Sobel's scheme uses the best algorithm to evenly cover the design space. However, it requires a large number to cover the whole design space. Monte Carlo is completely random and have poor coverage. I will be suggesting to use Latin Hypercube sampling, which uses a quasi-random approach. This sampling shows good coverage of design space with a small number of samples. You can try different number of samples. I will be suggesting to start with 1000 samples for design space exploration. After defining the settings, click here to update the samples for design space. Now, the tool uses its own algorithm to generate the required number of samples. Then, it uses machine learning models to make energy prediction for each samples. It is followed by associating the energy prediction results for each samples. Now, a web interface will be displayed to explore the design space. Here, on the left, you can find the energy scale for the given context. The first 20% of samples belongs to energy category A, next 20% samples to the category B, and so till category E. Next, you can find a slider to define the range of EUI which you want to explore. Move this slider and click here to generate the samples in the selected range. These samples are displayed here. Now, you can hover over these samples to know more about the value of other design parameters. After this, you can control the range for design parameters too. After selecting an appropriate range, you can click here again to generate the samples within selected range of parameters and EUI. Please see, only first 16 samples are displayed. Let's suppose you selected this sample. You can find its number here. Let's go back to Control Center. Go to Sketch Samples. Enter the exact number you want to sketch. Click Sketch Sample. Now, the footprint of the selected sample is drawn here. You can use those lines as guide to create the mass model. Now, let's move to Analyze option. First, we need to see how to model a design option in Revit. The model means only the mass model of the building. Other numerical design parameters we will see later. We may be creating multiple options. So, let's use Revit feature to manage all design options. Click here to open the Design Options window. Click on New to create an option. And click here on Edit selected to start creating a mass model. Please make sure you are creating a mass model inside a design option only, not in the main model. You can close this window and check here to see the currently active option or change active option. It is better to use Floor Plan View to create a building footprint. After switching to Floor Plan View, go to Massing and Site tab. Choose In Place Mass. Give any name, click OK. Now, you can sketch desired building footprint using sketch lines. Or you can use already sketched lines. Please draw the sketch inside these line constraints. After creating a closed loop for footprint, click here to create three-dimensional mass. Now, it is better to switch to 3D view by clicking here. You can define the height of the mass by selecting its top plane and moving it up or entering the required height here. Click on the Finish button to exit the sketching environment. Now, let's define the mass floors. First, define the levels. There are already 5 levels defined in the model. You can change the height between the floor as required. Go to any section view, select an appropriate level, and enter the required height. Please see, the levels are only active in the main model. Switch to the option, select the mass, click Mass Floors, and select the levels at which you need a mass floor. Now, you can see these mass floors. You can also see the total floor area here and more relevant details. Well, we have created a mass model for a design option. And let's proceed to its energy analysis. Go back to the Control Center. Focus on the section for Settings for created options. Select an appropriate option from the list. Click on View Edit Parameters button to open the Probabilistic Parameters window. This is the same form we used for design space exploration. We can define the values of each design parameters along with uncertainty. Or we can load parameters using these buttons. Define appropriate values and submit. Select the number of samples for the option. It can be different from the number of samples we used for design space. Usually, we found 200 samples, and Latin hypercube sampling is good for this analysis. After defining settings, click on Update Samples to create samples and run probabilistic energy analysis. It is required to update the samples after changing the values of probabilistic parameters. Once the background tasks are complete, click on Analyze option button to open web interface. The Analyze option function provides information about the performance of current design option in the context of the design space. As you can see here, we have the energy scale from the design space. And this box plot shows the performance of the current option. You can hover over this box plot to find more information about the uncertainty in the predictions. The useful information here is this 95% confidence interval and number of samples which are better and worse than the current option. Like this option, performs better than 408 samples and worse than 517 samples. Now, let's move on to compare options. This functionality is used to compare multiple options for their energy performance. Let's assume you have created a few design options, such as there's 5 options, and want to know which one is better. Open the Control Center. Go the section on Settings for created options. Choose an appropriate option, define its probabilistic parameters as we have done earlier. Different options can have different probabilistic parameters. Define the parameters for each option. You can click on Update Samples for each option separately, or after defining the settings, click on Compare Options directly. Now, the tool will update the samples for the options for which the samples were not updated already. Wait for a minute or so. After completing the energy analysis, the tool will open the web interface. In this interface, we can find all the design options we have created and the probabilistic energy predictions. You can hover over these box plots to know more. In the bottom section, we have results from statistical analysis. These values here shows while comparing the box option with L option, there is more than 95% probability that box will perform better. However, when comparing L and T, there is no difference. We can reduce the uncertainty to make more clear distinction. Reducing uncertainty means providing more details. Let's move to the last function, sensitivity analysis. This functionality provides information about the effect of uncertain design parameters on the energy performance. Let's run it for this option and the same design parameters we used earlier. We can use this button sensitivity analysis to run the analysis and open web interface. These sensitivity numbers reflect standardized regression coefficients. More details can be found in the info document. These values here reflect the comparative effect. By looking at these bars, we can say permeability has the highest influence on EUI. The negative or positive value shows negative or positive correlation, which means increasing permeability will increase EUI. We can use this information to make the option more energy efficient. Like in this case, reducing permeability will likely to reduce EUI. More, we can reduce uncertainty and permeability to reduce uncertainty in EUI. Well, that's all with the functions of the tool. There is additional functionality called tracking progress. You can go to section Manage Stage to access this functionality. You can save the current option as a stage to track the design progress. Let's save current option. Now, we progressed in the design and able to reduce uncertainty. Let's reduce uncertainty in the parameters and save it as next stage. And let's repeat this step once more to create one more stage. After making 3 stages, we can click this button, View Progress, to access web interface. You can now see how the uncertainty and the energy prediction have been reduced by providing more accurate value of the parameters or the details. Well, that's all about probabilistic energy analysis using BIM and machine learning for energy-efficient building design. You can find more details inside the info document. You can write me on my email to know more about any function or details of the tool.